All right, can you guys hear me upstairs? Can you hear me upstairs? Can't hear me? Can't hear me upstairs? Can't Still can't hear me upstairs? What's going on, man?
Recording in progress.
All right, can you guys hear me? Can you guys hear me upstairs? Can you hear me? No? Yeah. Did the volume check work? Can you guys hear me? Testing. Can you guys hear me upstairs? Can you guys hear me upstairs? Okay, all right. So you can hear me now, Rush. So you can hear me now, Rush Metal. All right, excellent. Good. All right, see? Okay, very good. All right, great. Thanks, Rush Metal. All right, thanks, guys. Okay, so like I was saying, in life, you gotta encourage yourself. This morning I was feeling very discouraged when I saw the number of people in class, right? And even though we have what, 1, 2, 3, 4, 5, 6, 7 people. Here's the thing. I'll tell you something. You gotta understand, life is tough. But to have a successful life, you gotta be tougher than life. That's what happens with successful people. You know? Successful people are tougher than life. Simple. Right? You have a lot of people rise from the ashes, from nothing. Right? From absolutely nothing. Right? To become great. So you gotta encourage yourself, you gotta push yourself. Let me tell you something. Things are rough out there. Job market looks terrible. But you gotta look past today. You gotta look past now. Look into the future. Right? You gotta set yourself up for a great job. Forget about the job market. Focus on you. What are you offering? What are you offering? Build up yourself. Build up yourself. Do projects, right? Like I teach 2 courses, leading innovation, right? Leading innovation and e-commerce. And in those courses, I focus on entrepreneurship. After you graduated, do a startup. It's something solid to show to employers. Say, while I was waiting for a job, I did a startup. This is what we built. This is the demo. This is the prototype. This is the video. I wasn't sitting down idle feeling discouraged. I was preparing. I was out there doing. as building up myself, adding to my portfolio, adding to my skill set, adding to my ability to contribute, right? People want entrepreneurial managers. You used to have managers and you used to have entrepreneurs. Now people want entrepreneurial managers. These are managers who work for other people, but they take an entrepreneurial approach to their job, right? They're not just there, okay, keeping things going. No, they're innovating, they're finding new ways to do the job, right? Right? They're finding exciting ways to get the job done, to help customers, to move the company forward, right? To add to productivity, etc., etc., right? So don't let the job market get you down and let you stop coming to class, right? What's gonna happen when the job market bounce? Bob, job market, all this drama stops, and then now you're like, oh, you weren't prepared. You gotta prepare. You gotta prepare yourself. It's like I said, when you play cricket, you gotta swing at the ball that's coming, not the ball that's at your foot. Yeah. Yeah, man. So you gotta encourage yourself, come to class, keep coming to class. Right? We're gonna work on some projects in the summer. We're gonna work on a deep learning project in the summer. Publish a paper. A lot of students are publishing papers now. Yeah, it's adding to their skill set. It's helping them to distinguish themselves from the rest of the people, right? So let's work on the celebrity project over the summer. Now, like I said, the celebrity in module 13, image augmentation is going to be the basis of the exam. That program, know that program very well. Know that program very well. Run it, learn it, know it, understand it, be able to reproduce it, right? You're gonna have, I'm gonna use that as the basis of the final exam. Yeah? Right? Because I need to be able to make sure that people have been doing work, have been doing their own work. So know that program, image augmentation program, know it as the basis of know it as the basis. Okay. Know it as the basis of the exam, right? Is the exam's worth what? 20%? Right. So know it as the basis of the exam. Right? Because I'm going to use it for the exam. And then I'm trying to create what we call synergies. Synergies when you reuse stuff. Use one thing for multiple purposes, right? Out of one thing, you get many benefits, right? So we're creating synergies. So that code we're also going to use to, and what I'm going to do is I'm going to use it. If I happen to teach this course again, I'm going to use it as a project, right? But yeah, that image augmentation code, we're going to use it on the exam. And then we're going to also write some papers out of it. You don't have to stay with your current group, but we're going to form new groups during the summer. I'm going to write papers on face detection. Yeah. Right? One paper can be emotion detection, celebrity emotion detection, right? One can be celebrities across different races, right? One can be celebrities in interviews versus the red carpet, right? We can say, okay, on the red carpet, our red carpet face is more more standardized or bland? Or put it this way, do celebrities show more expressiveness, right, on in an interview than on the red carpet, right? So the point, is that here's the important thing to understand about deep learning, AI, machine learning, all of these things. Unless you go to a Caltech, MIT, Harvard, Stanford, you can't distinguish yourself. You can't sort of distinguish yourself. You can't sort of distinguish yourself unless you go to one of these super tech schools. Then you can't sort of distinguish yourself. You can't sort of distinguish yourself on technical content, right? So in other words, for example, if you go to UC Berkeley, Caltech, MIT, Stanford, then you write papers about how to improve accuracy, right? From 99.5 to 99.7% using super advanced deep learning techniques. If you go to a school like AUM, then you have to distinguish yourself on the application of deep learning, right? So meaning real world problems, interesting real world problems, right? Right? So you take a data set and you take some interesting real world you take some interesting real world aspects to it, right? So deep learning and psychology, right? Right? Deep learning and the psychology of interviews. And you write a paper, do celebrities are celebrities more expressive, show more emotion in interviews than red carpet, right? Than the red carpet, right? Right? Than on the red carpet, right? And then you say, okay, you collected 200 red carpet shots, right? 200 interview shots, right? Random shots. Right? And from the red carpet shots, you detected 4 emotions. And from the 200 interview shots, you detected 12 emotions. Right? Why do we care? Why do we care? Relevance. In research, I have 2 things, rigor and relevance. Rigor is something you address when you go to one of these super tech schools, Stanford, MIT, Caltech, right? How can you improve accuracy? Relevance. People like us, we deal with relevance, real world, application, right? What's the relevance? The relevance is people show their true selves when talking about themselves, not when being photographed, right? So that's one paper, right? Deep learning and the psychology of interviews. Then you have deep learning and race, right? Deep learning and gender, right? And you use celebrity. Again, you use the same celebrity data set. You collect one data set. And then the point is that if we have 10 teams, all right, let's not be overly ambitious here. I'd love to do 20 papers, but let's say we have 4 or 5 teams, right? Of people who are interested in writing papers, right? We're each collecting 100, and we share 100 pictures of some given celebrity, and we share pictures, right? We have one pool data set, deep learning and gender, deep learning and expression by topic, right? We talk about which match words with which match words with pictures, right? Which topics, which interview topics elicit the widest emotions, right? Do women express more emotions in interviews than men, right? So we're using deep learning as a basis for talking about psychology, right? And we're approaching topics in psychology in more interesting ways, right? 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 But yeah, so yeah, we can do some interesting things. All right. So we're talking about transfer learning. Let's watch a video on transfer learning. All right, this is from the course I actually did on Coursera, right? So while you're looking for jobs, improve your qualifications. Improve your qualifications. Yeah? Improve your qualifications. Improve your qualifications. Right? No, experience is not what you want. I have 21 certificates from Coursera. And some are what we call specializations. Some are short course. Some are, all right, so like this. This is a 2-3 hour course, right? This is on transfer learning. Taking a pre-trained model and fine-tuning it. Right? This is LLMs again. LLMs. Prompt engineering, LLMs. Again, fine-tuning a pre-trained large language model. Right? All of these. All right, so this is a course. These projects are like take me 2 or 3 hours. All right, so project courses take me like 10 to 15 hours, right? Right? The course, right? So all of these last 7 or 8 are large language models because that's my area of specialty. So I've gone into Coursera and specialized and really dug deeper into what I'm trying to do, right? You got to show people that you're really interested in the thing, right? By getting certified, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So these last 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, these last 9 things are about large language models, right? And I have 8 projects on 1 course. So like I said, the course took me like 10 to 15 hours, right? Yeah, 16 hours, right? And then I also have mathematics for deep machine learning. It's 3 courses, right? Right? Significant amount of time invested in, right? Lots of time invested. 3 months at 5 hours a week, right? So 50, 60 hours, right? That's one specialization. This is a specialization, right? 3 courses, about 50 to 60 hours. Introduction to statistics, right? 14 hours, right? Machine learning specialization, right? Doesn't say amount of hours here, but quite a few, right? Two months at 10 hours a week, right? Microsoft Azure data scientist, right? TensorFlow developer, right? 2 months at 10 hours a week, right? So I mean about 80 hours. Yeah. Now these took me years doing it. This is since this is for the last 4 or 5 years I've been doing this. But you know, you have to start somewhere and start building up, right? Deep learning specialization, right? 3 months at 10 hours a week, right? So over 100 hours spent on this, right? Natural language specialization, right? 3 months at 10 hours. Again, over 100 hours, right? Machine learning, quite a few hours. Data science specialization, right? 4 months at 10 hours a week. So over 150 hours. Data analytics specialization, right? 4 months at 10 hours, right? Yeah, so you have to invest in yourself. You have to invest in yourself. So this is over the course of say 3.5 years. Yeah, over say 3.5 years. Yeah. I did these specializations and courses. Right? But you have to invest. This didn't take this long, actually. This one I actually did in like 2 weeks. But what I did is I spent like 12 hours a day straight. Like 12 hours a day for 2 weeks. Like I did it super intensely. Still took out quite a bit of time, over 150 hours. Yeah. All right. Anyway, so you get the idea, right? Yeah, man, invest in yourself. do some certifications, which show that you have not just education, but skills, right? Because people used to want skills, then they say, okay, we want education. So first certificates, then they want degrees. Now they want both degrees and certificates. All right. Anyway, so the point is that the video that we're about to watch is actually from this course. These are two related courses: deep learning specialization and then TensorFlow developer specialization, right? Which is basically using TensorFlow in deep learning, right? The convolutional networks in TensorFlow, etc., right? Natural language processing sequences, time series. All right, very good. Let's watch this video. Oh.
So for example, maybe a neural network learn to recognize objects like cats, and then use that knowledge or use part of that knowledge to help you do. One of the most powerful ideas in deep learning is that sometimes you can take knowledge the neural network has learned from one task and apply that knowledge to a second task. So for example, maybe you can have a neural network learn to recognize objects like cats, and then use that knowledge or use part of that knowledge to help you do a better job reading X-ray scans. This is called transfer learning. Let's take a look. Let's say you've created a neural network on image recognition. So you first do the neural network, train it on XY pairs, where X is an image and Y is some object, a cat, a dog, a girl, something like this. If you want to take this neural network and adapt, or we say try, image recognition. So first do the neural network, train it on XY pairs, where X is an image and Y is some object in the image, a cat, a dog, a bird, something else. If you want to take this neural network and adapt, or we say transfer, what is learned to a different task, such as radiology diagnosis, reading X-ray scans, what you can do is take this last output layer of the neural network and just delete that and delete all.
All right, and so that should be the last output, right?
Last output layer of the network and just delete that and delete also the waste feeding into that last layer and create a new set of randomly initialized waves just for the last layer, and that now output radiology diagnosis. So to create the first
All right.
having created that network, what you now do is when transfer learning is swap in a new data set, XY, where now these are radiology images, and Y do diagnosis. You want to and what you do is initialize the last layer's weights. Let's call that WL and BL randomly And now we train the neural network on this new data set, the new radial process. You have a couple options of how you retrain the network. You might, if you have a small radiology data set, you might want to just retrain the weights of the last layer, just WLPL, keep the rest of the parameters fixed. If you have enough data, you could also retrain all the layers of the rest of the network. And the rule of thumb is maybe the last layer, or maybe the last 1 or 2 layers. But if you have a lot of data, then maybe you can retrain all the parameters in the network. And if you retrain all the parameters in your network, in this initial phase, you're training on image recognition is sometimes called pre-training, because you're using the image recognition data to pre-initialize or really pre-train the weights of your network. And then if you're updating all the ways after it, then training on the radiology data, sometimes that's called fine-tuning. So if you hear the words pre-training and fine-tuning in a deep learning context, this is what they mean when they refer to pre-training and fine-tuning weights in a transfer learning task. And what you've done in this example is you've taken knowledge learned from image recognition and applied it or transferred it to radiology diagnosis. And the reason this can be helpful is that a lot of the low-level features, such as detecting edges, detecting curves, detecting parts of objects, learning from that, from a very large image recognition data set, might help your learning algorithm do better in radiology diagnosis. It's just learned a lot about the structure, the nature of how images look like, and some of that knowledge will be useful. So having learned to recognize images, it might have learned enough about, just what parts of different images look like, that knowledge about lines, dots, curves, and so on, maybe small parts of objects, that knowledge could help your radiology diagnosis network learn a bit faster or learn with less data. Here's another example. Let's say that you've trained a speech recognition system. So now X is input of audio or audio snippets, and Y is some ink transcript. So you trained a speech recognition system to output transcripts. And let's say that you now want to build a wake word or a trigger word detection system. So recall that a wake word and the trigger word are the words we say in order to wake up speech control devices in our houses, such as saying Alexa to wake up an Amazon Echo, or OK Google to wake up a Google device, or Hey Siri to wake up an Apple device, or saying Ni Hao Baidu to wake up a Baidu device. So in order to do this, you might take out the last layer of the neural network again and create a new output node. But sometimes another thing you could do is actually create not just a single new output, but actually create several new layers to your neural network to try to enable Y for your wake word detection problem. And again, depending on how much data you have, you might just retrain the new layers of the network, or maybe you could retrain even more layers of this neural network. So when does transfer learning make sense? Transfer learning makes sense when you have a lot of data for the problem you're transferring from, and usually relatively less data for the problem you're transferring to. So for example, let's say you have 1 million examples for your image recognition task. So that's a lot of data to learn a lot of low-level features, or to learn a lot of useful features of the earlier layers in your network. But for the radiology task, maybe you have only 100 examples. So you have very little data for the radiology diagnosis problem, maybe only 100 X-ray scans. So a lot of the knowledge you learn from image recognition can be transferred and can really help you get going with radiology recognition, even if you don't have a lot of data for radiology. For speech recognition, maybe you've trained a speech recognition system on 10,000 hours of data. So you've learned a lot about what human voices sounds like from 10,000 hours of data, which really is a lot. But for your trigger word detection, maybe you have only 1 hour of data. So that's not a lot of data to fit a lot of parameters. So in this case, a lot of what you learned about what human voices sound like, what a components of human speech and so on, that can be really helpful for building a good wake word detector, even though you have a relatively small data set, or at least a much smaller data set for the wake word detection task. So in both of these cases, you're transferring from a problem with a lot of data to a problem with relatively little data. One case where transfer learning would not make sense is if the opposite was true. So if you had 100 images for image recognition and you had 100 images for radiology diagnosis, or even 1,000 images for radiology diagnosis, one way to think about it is that to do well on radiology diagnosis, assuming what you really want to do well on is radiology diagnosis, having radiology images is much more valuable than having cat and dog and so on images. So each example here is much more valuable than each example there, at least for the purpose of building a good radiology system. So if you already have more data for radiology, it's not that likely that having 100 images of random objects of cats and dogs and calls and so on will be that helpful, because the value of one example from image recognition task of cats and dogs is just less valuable than one example of an X-ray image for the task of building a good radiology system. So this would be one example with transfer learning. Well, it might not hurt, but I wouldn't expect it to give you any data. And similarly, if you build a speech recognition system on 10 hours of data, and you actually have 10 hours or maybe even more, say 50 hours of data for wake word detection, it may or may not hurt. Maybe it won't hurt to include that 10 hours of data to do transfer learning, but you just wouldn't expect to get a meaningful gain. So to summarize, when does transfer learning make sense? If you're trying to learn from some task A and transfer some of the knowledge to some task B, then transfer learning makes sense when tasks A and B have the same input X. First example, A and B both had images as input. In the second example, both had audio clips as input. It tends to make sense when you have a lot more data for task A than task B. All this is under the assumption that what you really want to do well on is task B. And because data for task B is more valuable for task B, usually you just need a lot more data for task A, because each example from task A is just less valuable for task B than each example for task B. And then finally, transfer learning will tend to make more sense if you suspect that low-level features from task A could be helpful for learning task B. And in both of the earlier examples, maybe learning image recognition teaches you about images to help with radiology diagnosis, and maybe learning speech recognition teaches you about human speech to help you with trigger word and wake word detection. So to summarize, transfer learning tends to be most useful if you're trying to do well on some task B, usually a problem where you have relatively little data. So for example, in radiology, it's difficult to get that many X-ray scans to build a good radiology diagnosis system. So in that case, you might find a related but different task, such as image recognition, where you can get maybe 1 million images and learn a lot of low-level features from that, so that you can then try to do well on task B, on the radiology task, despite not having that much data for it. When transfer learning makes sense, it does help the performance of your learning algorithm significantly. But I've also sometimes seen transfer learning applied in settings where task A actually has less data than task B, and in those cases, you kind of don't expect to see much of a gain. So that's it for transfer learning, where you learn from one task and try to transfer to a different task. There's another version of learning from multiple tasks, which is called multitask learning, which is when you try to learn from multiple tasks at the same time, rather than learning from one and then sequentially after that try to transfer to a different task. So in the next video, let's discuss multitask learning.
All right, yeah. So the idea is that by using a pre-trained network, we can leverage learning. As he pointed out, and as I was pointing out on Monday, at a very basic level, neural networks learn. At a basic level, here's basically what your shape, what your face is, right? This is your face, right? This is basically what your face is. Here's your face, right? Here's basically what your face more or less looks like, right? Yeah, more or less. Right? Right? Your face is really a set of shapes, right? Right? This is basically what your face is. Yeah. And so what do look, and so your face is essentially a set of lines. And what do neural networks learn? They learn how the composure of lines relate to a class. Yeah. So here's your face, and here's a house. So how does your face, how does a neural network know a house different from a face? Because the lines look different, yeah? Right? I mean, no matter how fancy you get, this is basically what a house comes down to. Windows, doors, walls, and a roof, yeah? Yeah? And so really, if a neural network can understand the difference between a face, yeah, and a house, then basically what it's understanding is how to recognize lines. And all that's happening with with face detection versus house detection, right? Face detection, house detection versus cats and dogs is just a different combination of lines, yeah? Right? And so, yeah, we can take that base model, for example, MobileNet, yeah? Yeah, take that base model from MobileNet, and we take the output, as he said in the video, at some average pooling instead of max pooling, right? At another dense layer. And essentially, this dense layer now is simply going to say, okay, so the base model knows how to detect lines, curves, circles, squares, rectangles, oblongs. Yeah, it knows how to detect edges and lines. Yeah, because again, that's really all a line is. Yeah. When we talked about convolutions, when we talked about convolutions, right? We talked about convolutions. Looked at convolutions. Right? looked at convolutions and max pooling. Yeah. And we said that this was a vertical edge or a vertical line. This is a horizontal line. Yeah. A horizontal line is simply where you have one color. You have inside the picture, you have a line of pixels of one color, and then a line of pixels with a different color, right? Yeah. That's all our edges. That's all our line is, right? 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 And so look where we saw where the kernel goes through the image, right? You move the kernel through the image and it detects lines and edges, yeah? And you can have different kernels, right? Because again, for example, instead of just having this kernel, right? You could have a kernel that looks like this. Right? Right? And here you're detecting diagonal shapes, yeah? Instead of just vertical or horizontal, you're detecting diagonals, right? And again, this would be right? 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 Or you could flip it. You could also have right? Right? And so you can detect these edges. And so essentially, what the base model has done is it's already learned how to detect edges and shapes, right? I remember edges are just shapes. Yeah, edges are just shapes. A circle is nothing more really than this. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? That's a circle, right? And so if you can put a combinations of diagonals and straight lines together, you can detect circles. Yeah. Right? So if you can detect horizontal lines, vertical lines, diagonal lines, right? And combinations of these, then you can detect any shape. And so by the time we take the output from the base model, what we're doing is we're looking at shape detection. And then when we add this dense layer, all we're saying is learn the specific combination of shapes that relate to cats versus dogs. That's all. But we already have a base model that recognizes shapes. Shapes, edges, lines, combinations of lines. Yeah, give you shapes. Combinations of lines give you shapes. Lines are simply edges. Lines are simply edges where the color changes, right? Where the color changes, that gives you a line. That gives you an edge. Color change gives you an edge. Edge equals line. Horizontal line, vertical line, diagonal line, right? 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 And if you can detect lines and shapes, then like I say, you add your dense layer, and this simply says this particular set of lines and shapes relate to this class versus this class, right? And that's essentially transfer learning, right? Now, by the way, for the project, I should have mentioned this. I was thinking about this last night. So here's how I'm going to grade the project. So like I said, I didn't mean for you to use transfer learning, but I can't punish you for using it. However, if you use transfer learning, then you get, first of all, it has to be appropriate. I will grade whether or not you use it appropriately. And secondly, I will, what will happen is that the transfer learning projects will get compared to the other transfer learning projects, right? So in other words, if you're using transfer learning and getting a much worse accuracy than other groups who use transfer learning, then that's going to hurt you. Make sense? If you created your own deep learning network and you get the best accuracy of the people who created their own deep learning networks, then you benefit, right? So it's all relative. It's all relative, all right? It's really what it comes down to. And in any case, the specific model is just a small part of the whole grading scheme anyway, right? Because deep learning is much more than developing a model. All right, people, remember, celebrity faces. That's the basis of the exam. Know this well. Know this very, very well, right? Know it very well. Know it very well, right? Or specifically, let's go to right, image. Okay. All right, this is embarrassing because I have the wrong thing here. Actually, I have the wrong thing here. Oh, no. Oh, yeah. Okay, don't worry about that. This is the right thing. Know this very well. Know this very, very well. Run it, learn it, understand it. Go through it over and over again. Know it very, very well. Tweak it, train it, modify it, right? Know the model very, very well. Know the model very, very well. And I mean, I'm not giving you the whole code to learn and know. I want you to understand the augmentation presets, right? Augmentation preset, the data generator. Right? Data generator and the model, right? So know those very well. All right, let's take some attendance. And I really need to run to the restroom. All right, let's see.